So today's topic is G value. This is an EPR spectra and d orbital splitting. So before going to the d orbital splitting, first we'll talk about the G value. So I have already made one video on G value. So again I'm going to give a little bit idea about G value. So there are three terms we have: GE, G perpendicular, G parallel. So GE means the G value of a free electron. G parallel means the electron density along XY axis. G perpendicular means the electron density along Z axis. So there are if the electron density is more in a Z axis, then G perpendicular is greater than G parallel and it's greater than GE. If the electron density is greater than XY axis, greater in XY axis, then it will become G parallel, G perpendicular and GE. So these are the two conditions which are possible. So in both the conditions, GE is coming at last. So always remember GE is less than G parallel and G perpendicular. So this is why, because of the electron which is present in the free electron which undergoes the delocalization. So the free electron undergoes the delocalization. So because of that reason, always GE is less than G perpendicular as well as G parallel. Okay. Now the electron density along Z axis. If the electron density, this is the Z axis and then this is the XY axis, X and Y, this is Z. If the Z axis, if the electron density along Z axis is more, then it will become G parallel is greater than G perpendicular. If the electron density along XY is greater, then G perpendicular is greater than G parallel. So here we have two conditions, Z out and Z in. So if we see the Z out, in the Z out, the Z axis undergoes the elongation. So because of that, the energy will be less. This is for Z out. And the Z in condition will be like this. So this is dxz, dyz, and this is dxy, this is dz square, this is dx square minus y square. So here this dz square, dx square minus y square, dxz and dyz, and this is dxy. So what's happening here? When we are talking about Z out, in that case the XY axis gets compressed and the Z axis gets elongated. So because of that, the distance between the central metal atom and Z axis again is high. So due to that, the Z axis is more stable. That's why the more stable one will be having a less energy. So in case of Z in, what happens? The XY axis undergoes elongation, but the Z axis undergoes compression. So now the Z axis is very close. Because of that very close nature, they will be having some repulsions. Due to that will be having a higher in energy. So now take a D9 system. Just fill 9 electrons here: 1 2 3 4 5 6 7 8 9, and here also 1 2 3 4 5 6 7 8 9. So in this case, the along Z axis 2 electrons are there, along X and Y axis only 1 electron is there. So due to that, for Z out system, G parallel is greater than G perpendicular and then GE. So this is the for Z out system. Whereas for Z in system, here the zero number electrons, the number of electrons are 0, whereas here the number of electrons are 3. So in this case, G perpendicular is greater than G parallel, and this is greater than G electron. So this is the G value relationship for Z out and Z in system. And then we have a two joint distortion. We have the first one is a dynamic joint distortion, second one is a static joint distortion. So dynamic is due to unsymmetry in the T2G, and the static is due to unsymmetry in EG orbitals. So now, in case of dynamic jointal distortion, this is not permanent jointal distortion. So this is the temporary. It's temporary because the electrons which is present in T2G orbitals, which is in between axis, whereas the electron which is present in EG orbital, they're along the axis. So because of that, if the unsymmetry is there along the axis, so there more unsymmetry is there, then this will be comes under the static jointal distortion. So this is the permanent jointal distortion. And then, so this dynamic jointal distortion is called as isotropic system, and static one is called anisotropic. So for isotropic system, G parallel is equals to G perpendicular is equals to Z electrons. The electron density along all the axis is same for dynamic jointal distortion, compounds which show dynamic jointal distortion, and the compound which shows static jointal distortion, in that case G perpendicular is greater or lesser than G parallel and is equals to, it's less than GE. So this is for anisotropic system. If they ask for isotropic system, isotropic system, all G parallel, G perpendicular, GE is same. For anisotropic system, there will be an anisotropy, and this is the permanent one. And dynamic jointal distortion we'll see only at the low temperatures, and static jointal distortion we see at the low temperature as well as high temperatures. So this is about the G value. So now we'll go for the d orbital splitting, and now we'll apply the G value for d orbital splitting. So first we'll go for octahedral complexes. Okay, now the splitting will be like this. This is dxy dyz is equals to dxz. This is dxy, this is dz square, sorry so octahedral complexes. Here dxy, dyz, dzx, and this is dx square minus y square and dz square. So here we can't say which is a G parallel and which is the G perpendiculars, because the octahedral complexes comes under the isotropic systems. So because of that, here we can't apply the G value for octahedral complexes. Similarly for tetrahedral complexes also. So now we'll go for the square planar complexes. So the splitting pattern is very, very important. It's very easy to remember. So this is metal atom. So this is 1, 2, 3, 4 ligands are present. So now this is x-axis, and this is y-axis, and this is z-axis. So along x and y-axis there are 4 ligands are present. Along z-axis 0 ligands are present. So that's why so where the more number of the ligands are present, so there where more number of ligands present, there more repulsions will be there, more repulsions, and that will have higher energy. So this we need to remember. Since along z-axis there is no ligands, so that's why this should be lower in energy. So here we have dx square minus y square and dz square. In square planar complexes, dz square comes here because there is no electrons, sorry, there is no ligands along z-axis, and this one will be dx square minus y square. And now along here, if we see these two, dyz, dzx and dxy, so dxy will be having a 4 ligands, whereas z-axis is having 0 ligands. So because of that, it will exist like this. So dxy is here, and dyz and dzx. Now if they ask energy, where energy of these systems, so higher in energy is less stable, so this will be having higher energy and this will be having a low energy. Just remember, high energy less stable, less energy more stable. So now, so we have a D9 system here. We'll take D9 system. So now we'll fill the electrons here. So 1 2 3 4 5 6 7 8 9. So for square planar complexes, see here in the z-axis 2 electrons are there, 2 electrons along z-axis, whereas xy axis only 1 electron is there. Now apply the g value here. The g parallel is greater than g perpendicular, and it's greater than ge. So this is for square planar complexes. So because in case of square planar complexes, the 2 electrons are present in dz square orbital and 1 electron is present in the dx square minus y square that orbital. So because of that, g parallel is greater than g perpendicular. Next we'll go for the square pyramidal. So now here along z-axis 1 ligand is there, along xy axis 4 ligands are there. So it is also square pyramidal, also similar like square planar. The only thing is this one, the dz square will go up, dxy comes down, because here in along z-axis we have only 1 ligand, but along xy axis we have 4 ligands. Even though here, wait, I will write this first, dx square minus y square, this is dz square, this is dxy, dyz and dzx. So along x-axis, along x and y-axis 4 ligands are there, along z-axis only 1 ligand is there. Still the energy of dz square is greater than dxy. This is because, so we know that T2j orbital is present in between axis, whereas EJ orbital is present along axis. So because of this reason, even though one ligand is present along z-axis, so that will be having more repulsions. Due to that, the energy of dz square will increases. So for this also we can write energy order. This is the least energy, this is the higher energy. Now we'll take a D9 system. 1 2 3 4 5 6 7 8 9. So here also g parallel is greater than g perpendicular and it's greater than ge. This is for square pyramidal complexes. So now we have 2 more systems. We have a trigonal bipyramidal system. This is very, very important. So this is z-axis, this is x-axis and this is y-axis. Now see, along z-axis two ligands are there. Okay, so now the energy will be like this. This is energy barrier. So this is dz square and this is dxy, dx square minus y square, dxz, dyz. So here why this dx square minus y square and dxy means I'm talking about this dx square minus y square. Why the dx square minus y square is a less in energy, and here the main thing is there are two ligands which are present along the z-axis, but we can see along x and y axis. Individually we can see from the x and y axis. So along x-axis there is only one ligand is there, along z-axis there is only one ligand is there. So this is the reason why the dz square is having more energy compared to dx square minus y square. Along the z-axis there are two ligands are present. Due to that, this is having a higher energy. Now we'll take a D9 system and we'll see 1 2 3 4 5 6 7 8 9. So for trigonal bipyramidal system, G perpendicular is greater than G parallel and it's greater than GG, because there is more electron density along the dx square xy axis compared to dz square. Now we have one last system, pentagonal bipyramidal system. So just remember, pentagonal bipyramidal system as well as trigonal bipyramidal system, both are same. Here also we have dz square, xz is equals to dx square minus y square. The only difference is, so the pentagonal bipyramidal system and trigonal bipyramidal system almost same, not completely, almost same. The only difference is here in this case dxy, dx square minus y square energies are negative, whereas here these energies are positive. They are above to this barycenter, here below to the barycenter. This is the only difference. So this is about the d-orbital splitting. This is a very important topic, d-orbital splitting. I just applied a G-value for this d-orbital splitting. So if you have any doubts regarding these two topics, you can write in comment box, and if you like my video, please subscribe to my channel and also forward to your friends, and thank you.